Okay, good morning, good afternoon, good evening, everyone, and welcome back. As you can see, there is a plan for today's lecture on your screens. I hope that you can see the whole thing because I always try to cram too much on this first slide. So the last line may be cut off depending on how is your screen set. So the plan for today is to prove what I promised last time, which is a version of Kiesler's classical result from the 60s. He didn't prove this, but as I said, it's a version. The version that we care about is that in some model of ZFC, all ultra powers of a fixed separable C-star algebra are isomorphic. And when I say all ultra powers, I mean all ultra powers associated with non-principal ultra filters on N. For some mathematical reasons that have nothing to do with this course, I have to add this proviso unless ZFC is inconsistent, because if it is inconsistent, then there are no models of ZFC at all with any properties, and we cannot prove that it's consistent. So we just have to say that, but no worries. Now, today I'm basically covering parts of chapter 16, in particular 16.6 and 16.7, but not all of them. I'll come back and cover more of them. Probably in the next lecture. So just to recap what we said last time, we would like to extend the back and forth method to the uncountable. And Cantor's back and forth theorem just does not work for uncountable dense linear orderings. They're both trivial counterexamples and fairly deep counterexamples. But again, that's of no concern for us here. All that we need to know is that something goes wrong if you like to go beyond countable. So the plan for today, first explore a very simple abstraction for extending partial isomorphisms. Second, introduce Aleph-1 and the continuum hypothesis. I understand that for many of you this is not necessary, but we'll have to do it. And finally, use model theory to analyze what isomorphisms between non-separable C-star algebras look like, because that will give us an idea of how an isomorphism can be constructed. Now, you see, when I'm saying all this, I'm assuming that there is no obvious isomorphism. Because if there is obvious isomorphism, you don't have to construct it. You just define it. You just say, well, here it is. But in case of ultra powers, there is no hope that if you choose two different ultra filters on natural numbers, that you have a definition of an isomorphism between two ultra powers associated to them. Instead, you'll just have to construct it by recursion, and that recursion probably goes by constructing piece by piece. And basically, what that means is constructing its restrictions to separable subalgebras, and we'll just prove a slightly more precise version of that, just so that we can see that really what we are doing is in some sense necessary to construct these isomorphisms. All right, so let's go. So first, let's see what obstructions one can encounter when trying to extend partial isomorphisms. So here is an example by John McCarthy, been credited to him. It appears in the paper by Phillips and Weaver, in which they constructed non-trivial, outer automorphisms of the Calkin algebra. It's stated in terms of subalgebras to the Calkin algebra, but it works for many C-star algebras. So example says that there are separable subalgebras, A subalgebra of B subalgebra of Calkin algebra, and an isomorphism from A to Q of H that does not extend to an isomorphism of B into Q of H. Now, just a disclaimer here, when I say isomorphism, it is not necessarily onto, which sometimes annoys logicians because, I mean, isomorphism should be onto, but it is just convenient to talk about isomorphism onto its range sometimes. And that is what we are doing right here. Okay, so let's see what McCarthy's example does. So here is, this is my Calkin algebra. Here is A, and here is B. They're both separable, so they're not to scale. They're much smaller than what my picture makes them look like. And here is the copy of Q of H in the range. So there is isomorphism from A into something, and you just, there is an operator here in B, such that you just cannot extend this partial isomorphism to extend that element in the domain. Now, what this example shows is that you cannot hope to just go constructing isomorphisms. You have to have something to lead you. And here is the trick. If U is a unitary element, then the cyst algebra generated by it contains units, so I don't have to say generated by it and the unit. And by continuous functional calculus, it's isomorphic to the continuous functions on the spectrum of U. Now, because U star is equal to 1, what that means is that, and U is normal, right? It's every unitary is normal. What that means is that for every element in its spectrum, it satisfies the same equation, right? So it's Z conjugate is equal to 1, which means that all of the elements of its spectrum belong to the unit circle. And this spectrum determines the algebra generated by U up to isomorphism. Now, for us, the interesting unitaries are those which have the maximal full spectrum. Spectrum is equal to the full circle. So if you have two such unitaries, then a function that sends one to the other is a partial isomorphism, right? So our A is going to be C star of U for some such U, and phi of U is going to have the same property. Now, what special unitary do we want? Well, in the Calkin algebra, there is a unitary which has the following property. Oops. The property that we need is, okay, so there is U, Q of H, unitary, such that for every V in Q of H, V squared is not equal to U. So U doesn't have the square root. So if you can find such a unitary, then you can just take U and take A to B cyst algebra generated by U squared, and phi sends U squared to U. Right, so this algebra is isomorphic to that generated by U because they're normal elements with the same spectrum. And if you take B to be the algebra generated by U, clearly there is no place to send U, right? Your phi of U would have to be a square root of, sorry, phi of U would have to be square root of U, but there is no such unitary. So all that we need is this, but for that, we just use what is in Bruce Blackadder's encyclopedia book called probably the most important single operator on the Hilbert space, and it is a unilateral shift. We'll be coming back to it, so I don't want to go into details right now, but just fix orthonormal basis for your separable Hilbert space H, and then look at the operator which just sends nth element of the basis to n plus first element of the basis. So it's just a shift of the coordinates. It is not a unitary in B of H, but when you mod out the compacts, oh yes, the spectrums. So Jan just asked why they have the same spectrum. Well, what is spectrum of U squared? So this is it's a great question. Thank you. So it is just by the spectral mapping theorem. It is a set of all T squared such that T is in spectrum of U, right? And because a spectrum of U is already T, this is again going to be T, right? So it's definitely U and U squared don't necessarily have the same spectrum for any unitary U, but if you choose unitary with the full spectrum, then yes, they have the same spectrum. Right. So once you mod out the compacts, this becomes unitary, and it is a unitary whose Fredholm index is -1. If it had square root, its square root would have to have Fredholm index of -1/2, but Fredholm index is always an integer, so it doesn't work. So it's a simple example, but tells us that we have to be careful here. Okay. Oh, here. Okay, so let's go back. I mean, there are many.
Can you spend just a few words on Fredholm index, or it's too much of the tour?
It is not the right moment. I would be happy to say more about it, or maybe Said can say more about it in tutorial. But it is just not just basically for now. Just trust me that essentially I can say one word about it. So that there is a group homomorphism from the unitary group of the Calkin algebra onto the integers with the addition. Okay, so Say just said he can do that. So basically, to every unitary in the Calkin algebra, you can associate this number, natural number, which is Fredholm index, and this is group homomorphism. And once you put it this way, then it is clear that you can find these non-extendable isomorphisms. It's very simple, but just basically it will be a digression. So I don't want to go into too many digressions right now. So actually, Matteo, you can probably read about it while I'm doing this. I think if you listen to me for the next few slides, you'll just die of boredom probably. So apologies to set theorists. I just have to do this right now. So I have to define Aleph 1. And here is a simple lemma. If you have two uncountable well orderings, so it's by orderings, I mean linearly well-ordered sets. And each one of them has the property that each proper initial segment is countable, but they're both uncountable, then they have to be isomorphic. Proof is just Zorn's lemma. Just look at partial, I mean, look at partial ordering of all isomorphisms between their initial segments, proper or not. And just check that if you have a chain of such partial isomorphisms, its union is again a partial isomorphism, right? As a set theorist, I identify a function with its graph. So union of functions that agree on their domains is a function. And basically, Zorn's lemma shows you that you must have in general, if you have two well orderings, one of them is isomorphic to an initial segment of the other, but if they have this property, then it cannot be a proper initial segment. All proper initial segments are countable, but they're both uncountable, so the isomorphism has to go all the way up. Now, I will use this as my definition of Aleph 1. Aleph1 can be defined in different way, and actually I'll define it in a different way soon. But just for now, to me, in this course, it will be most convenient to just say that Aleph1 is uncountable, is basically order type of an uncountable well ordering, all of whose initial segments, proper initial segments, are countable. Right, so just think of it as equivalence class of all of those orderings under isomorphism. Now, the elements of Aleph1 are, well, we define them to be countable ordinals. So Aleph1 is the set of all countable ordinals, and countable ordinals are again well-ordered linearly ordered sets, and therefore comparable, right? So they form well ordering, and the type of that well ordering is Aleph1 again. Okay, so we'll be using this as index set to construct isomorphism. Now, here is the continuum hypothesis. Two sets have the same cardinality, and here is the notation. We just write this is not absolute value, it's cardinality. If there is a bijection between them. Now, there are many nice classical theorems like Schroeder-Bernstein theorem, but we just don't need that. I just need this definition. And now I'll also write Aleph1 to denote the least uncountable cardinal. Now, even to talk about the least uncountable cardinal, I need axiom of choice. Axiom of choice is actually equivalent to the assertion that if you have any two sets, then cardinality of one of them is equal to cardinality of a subset of the other one. So you have or partial ordering on all sets respect to cardinality. Axiom of choice implies that this is a linear ordering, and I'll be assuming axiom of choice throughout, but I just have to say this. This is definition of Aleph1 as a cardinal. But I mean, don't worry. Basically, there is not going to be any clash between thinking of Aleph1 as a cardinal and it as an ordinal, right? So ordinal is for counting, and cardinal is for measuring cardinality. Now I write C for the cardinality of the set of real numbers. Many important mathematical objects have exactly this cardinality. So here is a non-exhaustive list. So okay, this E is off. Let's just quickly see. So it's real numbers, complex numbers, power set of natural numbers. Now this is abelian C-star algebra. Actually, continuous functions on any x if x is compact metrizable, has cardinality C separable infinite dimensional Hilbert space, L infinity of n, L infinity, big L infinity of Lebesgue measure, or any probability standard measure space, the algebra of all bounded linear operators on Hilbert space, the Kalkin algebra, the sigma field of Borel sets of real numbers, and if you take your favorite separable C-star algebra A, then A, its multiplier algebra, typo, and it's a corona if A is non-unital. They all have cardinality continuum. And last but not least, it's actually going to be important later on. The set of all formulas over A also has cardinality continuum, which is somewhat annoying because in logic it is very important to work with countable languages. This language is uncountable. It is not a big deal, but it is slightly annoying. So I'm not proving any of these. Proofs are easy exercises if you haven't seen them. I'll actually prove that something has cardinality continuum later on today. And you can basically take that as an idea. Right, so basically Kessler's theorem talks about structures of cardinality continuum. Now, continuum hypothesis postulated by Cantor somewhere in the late 19th century, well, when it seemed to make a lot of sense. here two equivalent formulations. First one, for every set of real numbers, if x is uncountable, then its cardinality is maximal possible, the same as cardinality of the continuum. Second, every set of cardinality continuum has a well ordering such that every proper initial segment is countable. Namely, it is exactly well ordering of type Aleph1. Now, 2 implies 1 is an easy exercise. Just well order the reals. You just need to know that you can well order reals in such a way so that, of course, it's uncountable. Every proper initial segment is countable. Now look at subset of the reals. So here reals in that well ordering. Well, if that subset is bounded in that well ordering, it is countable. If it is unbounded, it is uncountable. End of the story. So 2 implies 1. Now, if you want to prove that 1 implies 2, and if you haven't seen this before, you'll see that it is something is non-trivial. And the point is that that implication requires not full axiom of choice, but some form of the axiom of choice. Basically, you need to know that you can well-ordered reals. That is all you need to know. But I should say, although I am accepting axiom of choice in this course and in everyday life, one of the most important models of set theory is a model in which axiom of choice fails. And out of these 2 statements, first one is true and the second one is false. So these are equivalent, but I mean, if you're a set theorist, you know that I'm talking about a model called L of R. But in one of the most important models of ZF, these are not equivalent. So continuum hypothesis is both true and false, depending on what you mean by continuum hypothesis. Right. So anyway, so for us, the useful formulation of continuum hypothesis is the second one. So whenever you see a set of cardinality continuum, it has a well ordering. No, it's what that ordering is defined by using Zorn's lemma. It's badly non-definable, and it has the property that all of its initial segments are countable. So if you're trying to prove something by recursion about that structure, all that you need to be capable of is somehow handle sets of size continuum. Oh, no, that wouldn't work, sorry. You have to be capable of handling countable sets. Right, so as long as you can handle countable sets, you're in good shape to prove things about these. All right, any questions? One more definition. The density character of a topological space is the least cardinality of a dense subset. So in particular, this density character of A is Aleph 0. It's exactly the definition of saying that A is separable. And here is the theory that I promised. If A is separable in infinite dimensional C algebra, then its ultra power has density character continuum. Here U stands for any non-principal ultrafilter on natural numbers. So you can add all of these to that list of objects of cardinality continuum. I didn't because if you go back to that list, all of those are nicely definable objects. Ultrafilters are not nicely definable objects. The existence of ultrafilters, again, requires some form of the axiom of choice. So they really belong to a different world from all of those elements listed on the previous slide. Okay, so let's see how can we prove this. Well, first point is look at a set of all finite binary sequences, right? So what I mean by that is empty sequence 0, 1, 0, 0, 0, 1, and so on, right? So all finite sequences of zeros and ones. This is a countable set. basically, to prove that, you just list them in lexicographic order. There are only finitely many sequences of any fixed length. So union of finite sets is countable. And because of that, this is a countable set. Now, second bit is that again, like so many of these statements, this is not about C-star algebras. All that we need to know is that A is a metric space which is not compact. Or actually, no, I'm assuming it was complete. You want A to be metric space which is not totally bounded. So that's all that is needed to prove this lemma. So what that means is the following. Oh, actually, I had to be careful here. You want a unit ball of A not to be totally bounded. And remember, this was my notation for the unit ball, all elements of norm at most 1. So it is not totally bounded. And if you forgot the definition, I'm going to write it right now. So what that means, i.e., there exists epsilon greater than 0, and let's call it D subset of unit ball, which is countably infinite, and the distance between any two elements of D, now my distance is given by norm, is greater than epsilon for all DC in D, well, as long as they are distinct, of course. If they're equal, this doesn't work. Now, if you know some functional analysis, you know that it is silly to say that. We can actually make sure that epsilon is as close to 1 as possible by one of the statements called the Reese's lemma. But it doesn't matter. Basically, it's really, this is about non-totally bounded metric spaces. It makes no excuse me, difference for us here. So we go on. Now, of course, I risk by posting these slides, if somebody just looks at the slides and doesn't listen to lecture, they may wonder, why is this guy teaching this course if he doesn't know functional analysis? But I don't care. So it's, I know about Reese's lemma. I don't need to use it right here. Okay, so we have this D. And now what I want to do is enumerate D, but not with natural numbers, but with these sequences. So enumerate D as ds for S, a finite sequence of zeros and ones. Okay, so now look at infinite sequences of zeros and ones. Okay, sorry, this is, I should probably write this so that it's readable. So it's supposed to be a razor. Here. Okay, right. I guess now it's clear. So look at sequence from natural numbers to 0, 1. F restricted to any natural number n belongs to this for every n. Right. So I'm just using. Oops. I'm just using the standard identifications that set theorists use, that every natural number is identified with a set of small natural numbers, which is a von Neumann's convention. Okay, so we have this. And now let AF be the following, be D sub F restricted to n and goes from 0 to infinity. Right, and now I think of this as an element of L infinity of A, right? So this is why I needed to know that all of these belong to the unit ball, right? So this is a bounded sequence. Now, if F is different from G, then set of all n such that the distance, D was a bad choice. Actually, no, I don't need to use D. Such that the norm of df restricted to n minus dg restricted to n is less than epsilon half is finite. In particular, it doesn't belong to the ultra filter, right? That's all I need really, right? Which means that distance of, I'll write here AF modulo U, although most of the time I identify representing sequence element of ultra filter here. I just want to be slightly more precise. So distance, not distance, again, this is the norm. Norm of this minus AG minus U is greater than epsilon half. So what this means is that at this set AF mod out U for F in 0, 1 to n is a subset of the ultra power of U of cardinality continuum, right? Because continuum is, I never said this, I guess, 2 to all F0, right? So the cardinality of this set of infinite binary sequences, right? So what we have is that cardinality of ultra power is at least C. The other way around, this cardinality is less or equal than cardinality of L infinity of A. And this one here has cardinality continuum. I should just say here that there is a warning sign. This uses axiom of choice very seriously. You know, to say that cardinality of quotient is smaller than the cardinality of the regional set, you really need to be able to choose, to have some selection function. And quite often definable cardinalities of quotients are much higher than definable cardinalities for regional sets. And this is an entire field of descriptive set theory, but we are not going there right now. So let's not worry about that. Okay, so right now we have just seen that ultra powers, all the ultra powers that we care about have cardinality, density character continuum, and therefore by continuum hypothesis density character F1. Okay, so in trying to prove Kessler's theorem, what we need to do is somehow prove isomorphism between algebras of density character F1. And our next task is to try to see what such isomorphisms look like, how they can be constructed. Any questions so far? Georgios? Yes.
Yeah, So sorry, just a tiny comment. I guess this result that you have stated is about talking about the density character of A to the U, right? The ultra power. And basically, your arguments before showed that the cardinality of that is continuum. But I guess by the epsilon over 2 separation, it follows for the density character as well, right?
Exactly. Thank you. Yes, exactly. So sure. Thanks. I forgot what I was proving. Yes. So let me fix that here. Basically, exactly. Essentially, this here shows right that density character. Oops, my chi. Sorry. Now I have a Greek. I have two Greeks in the audience, so I better draw chi properly. I hope this is acceptable. So density character is at least Aleph1, and on the other hand, this bound is actually what I wanted to do. Even cardinality is less or equal than C. So actually, why did I say Aleph1? I should have said continuum here. Right, that's what we proved. So in particular, what this shows, and thanks again, that I don't need cardinality sign here, that density character of ultra power is equal to cardinality of ultra power, and it's equal to continuum. Right. So for these guys, you have that. Note for separable C-star algebras that there is a gap. Density character is countable, but cardinality is continuum. Thanks. All right. Okay, so let me just say a few words about one of the great techniques that C-star algebraists know, so-called approximate intertwining, or also called Elliot, after George Eliot, of course. Elliot intertwining. It is amazing technique. If you want to prove that two algebras are isomorphic, and if they're given some sorts of inductive limits of something, I guess what I'm going to say is an old-fashioned view of intertwining. Then you construct an isomorphism between A and B by doing this. But by going back and forth between A and B, but not back and forth precisely. Each time you go back and forth, you allow your images to move. So for any element of the domain algebra, its images are under these functions, this chain of functions that you're constructing, form a Cauchy sequence. So they're not constant, but they converge to something. And you just assure that that happens for each element of A. Same thing happens for each element of B. So in the end, all of those Cauchy sequences have limit. These are complete metric spaces. And those limits define a function and its inverse. Now, if this doesn't sound like a big deal, you should take a look at some of the papers from the subject. It is amazing how with very little information, one is capable of finding isomorphism between algebras A and B. You're just given some countable group and it tells you where elements should go approximately. Eventually, by the time you exhaust the whole algebra, you tweak the images enough to get isomorphisms. And it's natural to ask, well, would approximate intertwining help us? Now that I told you about this great technique, all that I have to say here is that it is of no use in our context. So what I mean by that, if A and B here are of density character Aleph1, which means that your sequence of these partial isomorphisms, unless some of them are uncountable, which is probably not going to happen. So this sequence actually has length Aleph1. So for each element A here, you have Cauchy sequence inside B, but Cauchy sequence, or Cauchy net, actually I should say Cauchy net, indexed by Aleph1 with this natural ordering. Well, the fact is that any such Cauchy net in a metric space, it is eventually constant, and therefore it's convergent. Now the reason for that is that there exists alpha n less than Aleph1, so that for all beta greater than alpha n, if you look at x beta minus x alpha n, I'll just write a norm, right? So my Cauchy, but my complete metric space is just C-star algebra, so that distance is 1 over n. Right, so from this point on, everything falls into 1 over n open ball around that point. But now you just take supremum of all Aleph n's, call it alpha. Well, supremum of a countable set of countable ordinals is still countable. But now, what does this tell us? For all beta greater than alpha, x beta minus x alpha is equal to 0, right? So it's less than 1 over n for any n. So everything collapses, and what this means for us practically is that if you're constructing such an automorphism by back and forth method, basically after countably many steps, you have to make up your mind. You just have to stop moving that point, because if you continue moving it, something is going to go wrong. You will not construct isomorphism. Pedro has Aleph 0 should be an Aleph 1. That's absolutely correct. Yes, thank you, of course. Thanks, Pedro. Right. So okay. So basically, the rules are completely different from the rules in separable worlds. And actually, I would say that the results from Elliott's program are much deeper than what I'm saying right now. Basically, we just have to have something that is going to lead us on the nose, to tell us exactly where things should go. And we'll see what it is soon. Right, so this is what I just said, written here. So if we have point norm-convergent net of star homomorphisms indexed by Aleph 1, then this is eventually constant. Okay, now to find this guiding light, we just go back to model theory. And let's just remember what were the definitions. F sub A is the algebra of formulas over some fixed East algebra A. If A is a subalgebra of C and B bar is some tuple, n tuple in C, then type of B bar over A is the functional, evaluation functional that evaluates values of formulas at B bar in C on this set. And B is an elementary submodel of C if these evaluation functionals all agree for any n tuple in B, whether it's evaluated in C or in B, you get the same value. Right, so, and so this is just saying that in different words. Now here two exercises. First one tells us that this is relevant to that little abstraction that we considered earlier. If A is an elementary sub-East algebra of B and U is a unitary in A, then U has a square root in A if and only if it has a square root in B. I should say that it should be obvious what the formula should be that describes this, but this is not completely trivial exercise. The reason is that if you write a formula, which, I mean, basically your first guess of what formula should be must be correct. A formula involves infimum, and you're saying infimum over something is equal to 0. Well, you have to prove that that infimum is attained. Right, so there is obviously a formula which tells you that there is something that is as close to being square root of U as you would wish it to be, but formula is supposed to say that there exists a square root of U, which requires a little bit of extra work. Second exercise requires some knowledge of some C algebra theory, but I'm just mentioning it because we talked about tracial states. Remember, states on C algebra are functionals that have norm 1 that send positive elements to positive real numbers. And tracial states have that commutation requirement, tau of AB is equal to tau of BA. It is not, okay, it is a nice application of Hahn-Banach theorem that every state extends to a state of the bigger algebra, but tracial states need not extend to tracial states. But if you have an elementary submodel, then this is true. So these two are two ways in which the elementary submodels are better behaved than arbitrary subalgebras. Now, we'll just have to sort of move this, to uproot this relation and to talk about elementary embeddings. So what is function between two C algebras is an elementary embedding if for every formula C and for every A bar of the approximate sort, here A bar is in A to the N, the values of these formulas, the evaluation at A and phi of A agree. So in other words, what is elementary embedding? Well, it is an embedding, it's injective, and the image of A is an elementary submodel of B. Okay, now you see C-star algebras form a category. There are several choices of morphisms between them. The most obvious one is star homomorphisms, but there are few other very important ones like completely positive contractive maps and few of those variations on that coming from analysis. But there is this one coming from logic. So C-star algebras under elementary embeddings this is a category. Composition of elementary embeddings is an elementary embedding. Also, identity map is an elementary embedding. So this is a very nice category, and it is in some ways much better behaved than category of star homomorphisms, right? So in particular, for example, that John McCarthy's counterexample doesn't work here because well, not only square roots, but any roots of unitaries, elementary embeddings are going to be correct about that. So you know, unitaries are going to respect this. It is still not completely clear what exactly elementary embeddings do and what they don't do, but they do for us what we are set to do, which is all that matters for now. So basically, the plan is to take a look at this category and see how what countable saturation tells us about the elements of this category. Any questions? From abstract elementary class point of view, it is better. It is elementary class, right? So I mean, these are C-star algebras axiomatizable. I don't know if this is what you meant, but this is as well behaved. I mean, this is a first order theory. So this is basically first order continuous theory with respect to elementary embeddings. So it beautifully behaves. So I would say it's better than abstract elementary classes in that way. Now, of course, you know, I use every opportunity to rant about this. I'll do it again. If we had this conversation 20 years ago, I would have said, and most people would have said, well, you know, this is not an elementary class because you don't have infinitesimals. When you take ultra power, you get some garbage, so it's hopeless. But then you know, these people came and found that actually there is a nice tweak on logic which makes it into perfectly fine first order logic with respect to which is as well behaved as classical first order logic. You have Lindstrom's theorem, you have all the classical results, and so we now see that this is elementary class. And it makes you wonder, are there some other elementary classes that we don't even, that we think are not elementary because we don't see what's the right language? No, it is amazing right now to look back and to realize that it took so long to see what the right language is, but it wasn't obvious. Okay. Now, here is another definition that I haven't mentioned so far, although it is the most basic definition in many ways. First, a formula with no free variables is a sentence, right? So what that means is that you're quantifying out all the variables. So for example, formula sup over all x less or equal than 1, sup over all y less or equal than 1 of the norm of the commutator x and y, if you give me a C-star algebra, you don't have to tell me where to evaluate it. You just evaluate it and you get a number. And this number is going to be either 0 or whatever it is in 2x2 matrices. So this formula, sorry, this sentence has only 2 possible values. And it tells you, is your C-star algebra a billion or not? There are many other important sentences, like one that tells you whether algebra is purely infinite and simple, whether it has projections, whether all sorts of things. So now that algebra, the sentences form an algebra over real numbers. And so the theory of a C-star algebra A is a functional on that algebra. So you can think of it as a functional, you can think of it as its kernel, that's how it's written here. So theory of A is a set of all sentences which evaluate to 0 in algebra A. So for example, this is going to be in the theory if A is a billion, and it's not going to be in the theory if A is not a billion. So theory tells you all first order information about your algebra, and right, so here it's saying also you can think of it as a kernel, you can think of it as functional. Now if you think about it as a functional, it's really thinking of it as type of the empty sequence. You see, this is something that is easily overlooked. When you're computing type of some element of C-star algebra, you evaluate all formulas that have 3 variables in that, but you also evaluate all sentences. They're part of a type. So type of any element actually in particular codes theory of the algebra in which you're evaluating it. And also in particular, if you just take empty sequence, you get exactly the theory. We say that A is elementarily equivalent to B and write this A triple bar if their theories are equal. Right. So the way to think about it is that this is a transformation from A into the character space of f of A. I'll write this for a set of sentences. So the dual space of this. This is not a functor. This is just a means of assigning functionals to algebras. And as such, it is a very crude invariant. It is smooth, which is really a technical term coming from operator algebras, going back to Glim, I think, maybe Efros later, because you have a nicely definable, basically Borel measurable, if you set everything in a proper way, function from the category of C-star algebras. You need to do some coding here, which I'm hiding under the rug, into a nice Polish space. Right, so the dual ball of this space is in weak star topology, a nice compact metric space, and equivalence classes are algebras which get the same invariant. So because it is such a crude invariant, it doesn't distinguish many algebras that are otherwise easily distinguishable. Let me just say a few words about that. Oh yes, right. Actually, before I forgot what was on this slide. This is very important. So for any two C-star algebras A and B, here is a useful reformulation that we're going to use. It's useful in that sense of elementary equivalence between A and B. A is elementarily equivalent to B if and only if for every type over the empty set. So here I mean type of some number of variables. T is approximately finitely satisfiable in A if and only if it is approximately finitely satisfiable in B. So this is an exercise, but since I am going to be using it, I should give you a hint. The point is that this notion, approximately finitely satisfiable, just refers to finitely many conditions from the type. So it's really finitely many formulas. You can collect them in a single formula. And then finite satisfiability just tells you what value of that formula is supposed to be. And actually, when I say formula, really you want to collect them in a single sentence. You want to quantify out this variable, this free variable x bar. And so from the value of that sentence, because A is elemental equivalent to B, you know that they are going to be the same in A as in B. So this is equivalent. Anyway, again, since I'll be using this, proof is available upon request. Okay, so here are some just to connect this with standard C-star algebras. C-star algebra is UHF, or uniformly hyperfinite, if it is unital and it is an inductive limit of full matrix algebras Mn of C. C-star algebra is AF, or approximately finite, if it is an inductive limit of finite dimensional C-star algebras. Now, there is, by the Artin-Wedderburn theorem from algebra, or by just proving it from the scratch, every finite dimensional C-star algebra is of the form, it is a direct sum of a few of finitely many full matrix algebras. Right. So the difference is in definition is just that building blocks in one case are just full matrix algebras. In the other case, that they are finite direct sums of full matrix algebras. And UHF algebras were classified by Glim in 1960, and in early 70s, George Eliot classified AF algebras by dimension groups, which are certain countable order groups. Now those invariants that were used are different. So the invariants for UHF algebras are smooth, and even basically you can see them from theory. So if you have separable UHF algebras, they're isomorphic if and only if they're elemental equivalent. So the theory can recover a K0 group of a UHF algebra. On the other hand, there are unital separable AF algebras A and B, which are elementally equivalent but not isomorphic. This is a consequence of the fact that we know exactly what AF algebras are. As I said, they are classified by certain countable discrete groups. And it is known that you need, I mean, basically those groups, those dimension groups are not classifiable by smooth invariants. And that is basically the proof, modulo checking that everything is Borel measurable. So this is really messy business to prove this, which is embarrassing because we don't know. We don't know a single concrete example of a pair of such algebras, although we know that I think it should be possible to prove that there are continuum many separable non-isomorphic AF algebras which are all elemental equivalent to one another. So that there should be large families of these, but we have no idea how to construct this. So I mean, if anybody has an idea how to prove this, it would be nice to know. Analogous remark applies to the Kirchberg algebras, which I'm not defining, but if you know what they are, it is almost equally embarrassing that we don't know that either. Okay, so here we have what theory can and what it cannot do for us. Now, go back to model theory. So here is so-called downward Lennonheim-Skolem theorem. Again, this holds in much larger context than for C-star algebras. If C is a non-separable C-star algebra, here's my C, it's kind of big, and X subset of C is countable, so here is this tiny X. Then there is a separable A elementary submodel of C, which includes X. So here is A. It's separable elementary submodel. This is, oh yes, I should say that to C-star algebras, a slightly restricted version of this is known as Blackadder's method. Basically closing off. You would just start from some countable subset of something big, and then keep on throwing enough elements to make it behave like the big one in a way that you want it to behave. I'm just going to sketch this, but here is the main point, the so-called Tarsky-Watt test, which says the following. So here we have A is the big one, B is the small one. So B is elemental equivalent to A. So I just realized that sometimes I'm using the one with equality, sometimes not. It's random, so I hope it's not confusing. I haven't realized until now. So I just mean B is elementary submodel of A. Oh no, actually in this case I had to say equal because of course lemma should be true even if B is equal to A. So I had to leave that possibility. So B is elementary submodel of A if and only for every formula phi and for every B bar in B. So B bar is some parameter here, which is of the appropriate sort to fit into phi in this spot. We have that if you take infimum over the unit ball of A of value of phi at xb, what you get is equal, or you just say greater or equal, it's equivalent. Oops, wait, A was the, oh no, sure, right. A is the big one, right? So it's greater or equal to the infimum over the smaller ball of B of the same thing. Now, it is important here that this is not a typo. You see, we are evaluating the formula only in the big algebra. So the only difference is quantification here, that one quantification is over the small ball, the other one is over the big ball. This is a simplification as compared to the actual definition, because in the actual definition, when you say that B is elementary subalgebra of A, then you have to look at arbitrary formula. Arbitrary formula has arbitrary number of quantifiers, and for each one of those quantifiers, in case of B, they're ranging over the ball of B. In case of A, they're ranging over the balls of A. So the statement is a bit messier. Proof of Tarsky-Watt test is just by induction on complexity of the formula. You just start with quantifier-free formulas. It's automatic, and you just prove that each time you're adding a quantifier, you can survive. But this is really tailor-made for adding a single quantifier. If you vary where is the soup, why we have just inf, well, soup is minus inf of minus formulas, so you don't really need both. So that would be a hint of why Tarsky-Watt test is true. Now, why is that enough? Well, you see, once you know this, then it's clear how closing off has to work. Well, okay, it's clear modulo one thing, and I should say more about that thing. I hinted at that before. Oh, why do I always hit the wrong button? Here, okay. So here is the idea. Once again, here's C, here's X. So what you want is evaluate all formulas as phi n in n, and just look at these infs. Oh yes, and also evaluate elements of X. as xn for n in n. Actually, what you want is something slightly better than that. You want to enumerate all possible tuples, finite tuples of elements of x, that you can end up really with enumeration of all possible combinations of this form, phi with, oops, this and with an extra variable here. And then you want to see what these infs are, see what is infimum in the big algebra, and just add an element which makes it as close to that infimum as possible. So you just need countably many elements to make infimum be as small as necessary. So as long as your language is countable, you just do this, produce a bigger set such that the Tarsky-Watt criterion will be satisfied as long as your B bar comes from X. But now you have a bigger set, which I can call X1. Now you have to enumerate all elements or tuples from X1 and again repeat the process and end up with set X2 and so on. So you just build this increasing sequence of sets Xn, so that if you have formula and parameters from the n set, then the infimum, whatever is infimum over the ball of the big algebra, it will be the same as the infimum over set xn plus 1, and just take union. Fortunately, you can just stop because this is all finitary. This is good enough. That closure of that set is automatically going to be a C-star subalgebra, and it's going to be elementary submodel. There is just one issue in what I said, which is the set of formula is not countable. Right, so as we said before, the set of formulas, new formulas over the empty set, this has cardinality continuum. Right, so what do we do? Well, the trick is that we defined before that norm on the set of formulas. So remember, norm of formula phi was supremum taken over all relevant algebras A and A bars of the evaluation of phi at A bar in the algebra A. Well, the fact is that in this norm, the space of formulas is separable. So F, okay, what to write? F empty set is separable in this norm. Again, proof by induction on the complexity. If you have quantifier-free formulas, just look at only polynomials that have coefficients in some fixed. Actually, I could put here A, so A is separable. Look at coefficients which come from some prescribed countable dense subset of A. That is a countable set, and it's going to be dense in the set of all quantifier-free formulas. And then, you know, when you're choosing continuous functions, right? At one point, remember, in construction of formulas, we had these continuous functions from R to N to R. Well, really, we care only about those functions whose support is compact, because always only those are being applied. And that set is by Stone-Weierstrass. We can take just the polynomials. So without loss of generality, G is a polynomial. But oops. But once you have just polynomials, well, again, you can just look at polynomials with rational complex coefficients, and then you have countable set. So one just checks that there is countable set of relevant formulas, And now the good thing is that evaluation is continuous with respect to this norm by definition. So if you take care of Tarsky-Watt test for a countable dense set of formulas and countable dense set of parameters, you're in good shape. You produced elementary submodels. So that's all. Okay, I admit that this wasn't really a proof, which was somewhat hand wavy, but again, I don't really want to go into these details in the official course. But I mean, in addition to Said's tutorials, I'll be happy to give an extra lecture with these proofs if there is interest in that. Just because some of the participants have seen this probably more times than they would care to have seen it. But as you know, the class is somewhat non-homogeneous. So okay. So that's Levenheim's column, and right. So we were here. Now, what this tells us is that we have the following consequence. If C is a C-star algebra of density character Aleph1, then you can write it as an increasing chain of separable subalgebras. Now, there are two remarks I want to say. Actually, okay, first I have to say why is that so? Well, you just start by applying Levenheim's column, right? Because C has density character continuum Aleph1, you can just fix a dense subset of size Aleph1, and then just take X to be first alpha elements of that set. Remember, alpha is a countable ordinal, union whatever was your alphath algebra, and just use Levenheim's column theorem to find separable elementary submodel. And by this bookkeeping, you just build bigger and bigger elementary submodels. You just make sure that the alphath element belongs to alphath elementary submodel, at least if you have successor ordinal, and exhaust the entire algebra that way. That's one thing, but actually you will not be able to make sure that the alphath element always belongs to the alphath. Let's say it belongs to alpha plus first element because of this very important requirement that this chain be continuous. Continuous means that at every limit ordinal beta, so limit ordinals are those which are supremum of small ordinals. C beta is actually inductive limit of C alphas. Now, what this means, because they are subalgebras, is that if you take union of all alpha less than beta C alphas and you take closure, you get C beta. Right? You have to take closure. But important thing here is that at Aleph1, you don't have to take closure. This is literally the union of those separable subalgebras. Why is that so? Well, if you have any Cauchy sequence, it is countable, and therefore it is included in one of these C alphas. So because C alphas are closed, limit is there as well. So C is literally the union of these separable subalgebras, and we'll actually be using this fact. Okay, so at this point, we have this sort of representation theorem for C-star algebras of density character F1. There are always unions of elementary chains of separable submodels, right? So this is called elementary chain. Actually, what you have is C0 is elementary in C1, elementary in C2, and so on. They're all elementary in C. This relation of elementarities is transitive, so it works this way. Okay, so now we just have to see how are we going to use this. Any questions? All right. So here is the exercise. Oh yes, right. So this is very important. I'll not be using it explicitly, but it is somewhat illuminating if you haven't seen it. So here we have A, which has density character F1, and you write it somehow as union of continuous chain of separable substructures, not necessarily elementary. Just somehow keep on, just throwing in more and more elements and generating separable subalgebras, exhausting everything by the time we reach stage F1. Now, you look at C prime, which is just those A alphas which happen for some reason to be elementary submodels, right? So once again, you're just throwing elements at random, generating separable subalgebras. And at the end of the day, just look at those ones that happen to be elementary for some mysterious reason. Well, it turns out that this is going to be not just non-empty, but it is actually going to be a continuous chain of separable substructures, and A is going to be union of this chain. So if you're a set theorist, you of course know that I'm talking about closed and unbounded sets, and that there is much more to say about this than just this, but I don't think I really need to go here. So I'm just basically throwing this as a hint, and you can take a look at it and or read more about clubs. Oh yeah, I should say that this kind of combinatorics is, well, much deeper, but basically this is the very beginning. Combinatorics of these closed unbounded sets is very important in the half of that theorem that I'm not proving, that in some models of ZFC there are many non-isomorphic ultrapowers. But that is a different story. Okay, so let's take a look at what an isomorphism has to look like, right? So remember, what we really want to do is we have A separable, we have two alpha powers, and we assume that there is an isomorphism between them. We assume it because we want to understand what would be its properties that would help us build the isomorphism. And here are some properties. Suppose that A and B have density character F1. Phi is an isomorphism from A on to B. So okay, so instead of A and B here, A ultra powers, I just have some two abstract algebras A and B. Then both A and B can be represented just like in the previous slide as increasing unions of countable chains of separable elementary substructures. A is union of A alphas, B is union of B alphas. But in addition, these two chains are related in the sense that Phi sends A alpha exactly to B alpha for each of the alphas. So you see, you start with something, with some isomorphism, and you just randomly choose chains of separable elementary substructures as guaranteed by the previous theorem, and most of them, in some sense, are not going to be sent to corresponding substructures of B, but on a large set, this is going to happen, which basically means that our idea of what most substructures really means is actually wrong. Let me sketch why this is so. Well, let's just A, B union, or let's say A alpha zeros, and B is union of B alpha zeros. These are just separable elementary substructures. And these are continuous chains. That's very important. All right, so now look at phi of A0. Well, it is probably not equal to B0, but this is a separable subalgebra of B. Now, separable means it has countable dense set. that countable dense set is subset of some large enough B alpha, but B alpha is complete. So phi alpha 0, image of alpha 0 is subset of some, let's call it B alpha 0. So there exists some alpha 0 such that this holds. Okay, now we look at phi inverse. Phi inverse of B alpha 0. Well, same story. This will be subset of some A alpha 1. And moreover, I can just make sure, if necessary, to bump it up and just assure that alpha 1 is greater than alpha 0. And now I go back. Phi of A alpha 1, again, image is separable, so it is subset of some B alpha 2. And so on. So I find alpha n for n in n increasing with the property that phi of alpha 2k plus 1 is subset of B alpha 2k. And moreover, if I look at the other formula, really what it says is that this includes B alpha 2k minus 2 for all k greater or equal than 1. Right? So if I'm just looking at this in the B side, I have an increasing sequence of separable subalgebras, separable elementary submodels even, B alpha 0, then phi of A alpha 1, then B alpha 2, phi of A alpha 3, and so on. So union of B alpha 2k is equal to union of phi of A alpha 2k plus 1. And it is, moreover, we know exactly what it is. And this is where this crucial assumption that the sequence is continuous is being used. This is equal to, why do I write the union sign? You have no idea. This is equal to B sub supremum of all alpha k. And this is a countable ordinal. But moreover, it is also, I can take supremum here and phi commutes with these unions. So this is phi of A sub supremum of all alpha k's. Right? So I'm getting actually even more than I promised. I'm getting the same ordinal, literally. Okay, so this way we get one that this set is non-empty. But look, I can just go back and just instead of starting with A0, okay, so let's do this in different color. So just fix any beta less than aleph 1. And instead of 0, just start with beta and do exactly the same process. Everything is still separable. And here I'm getting this still this equality. Right, so this proves that the set of those ordinals, okay, I used alpha and beta, so let's call it gamma, gamma less than aleph 1, with the property that phi of A gamma is equal to B gamma is unbounded in aleph 1. Right? Because for any ordinal countable, no matter how large, I found even larger one which was a fixed point in this sense. But moreover, because both sequences are continuous, this set is closed as well. So by closed, what I mean here is under soups of countable subsets, right? Because if phi of A gamma is equal to B gamma, for certain countable sequence of gammas, the same is going to be true for their supremum, because both sequences are continuous. And that's exactly what they promised to prove. So let's just go back, right? So what we get is we find these substructures, and phi sends A alpha to B alpha for all alphas. Now, what this shows is that if you want to construct this isomorphism between ultra powers, eventually what we are really doing is somehow producing these filtrations of those ultra powers into separable elementary substructures, and this pairing between those structures, which is isomorphism that extends all the time. So I guess, let's see, yeah, I guess I should probably stop at this point, and we can continue next time to see how exactly saturation helps us. I guess it should be, at least, it should be clear that saturation should be relevant to something like this, but we'll work out the details on Friday. Any questions? My iPad's battery survived, I think. I'm at 6%, okay. So, yeah. Okay, so there don't seem to be questions. Let me ask you a question. You see, I was really worried about today's class because half of you have seen this probably more times than you would want to have seen it, and another half hasn't. So I remember once I was giving a talk. It was one of my earlier talks in CIST algebra conferences, and I just assumed that this was obvious to everyone. And I was later told politely that what I was saying made no sense whatsoever. So I just wanted to make sure to say everything in some detail right now. I hope I managed. Let me know if both if I overdid explanations and if I underdid explanations as well. You know, basically, this is something that one who is interested in ultra powers just has to learn. And once you learn it, then it's easy. Like, I guess like anything else. So, okay, so it seems that there are no questions. Oh yes, I should also say thanks to those who sent solutions to homeworks, and apologies for typos. There were mistakes. Thanks to Pedro and Daniel for pointing out that I was asking silly questions. I'll prepare next problem set for Friday. I just wanted to see how you're doing so that I can see if I should make homeworks more difficult or easier or whatever. Yeah, so that's all for today. So stay safe and see you on Friday.